acceleration that's linear acceleration is equal to r times alpha, where alpha is angular acceleration. Or maybe right now for this first second, I'm going just kind of slowly, then I'm going faster and faster and faster, 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 faster. So you can say that's what alpha is, the angular acceleration. And that would correspond to a car, which would be maybe doing something like this, then this, then this, soon takes off, flies, you know.
It just keeps going.
Yeah. All right. So anyway, so there are those. There's one more item that just sort of upon reflection that you need to know, and that's sometimes we don't give this omega. Sometimes it's hidden information. Let me see if I can find an example. They're yeah, I guess I could. There's another way that things, when something is spinning or something is turning or whatever, there's another unit that they will give. Sometimes they might say the Earth rotates once per day. Believe it or not, that is an angular velocity statement. Okay? Omega, okay? How many radians over how much time period? Well, if the Earth rotates, think about the Earth on its axis, okay? If it's rotating once all the way around, then that would be 360, but in radians. 2 pi. 2 pi, just 2 pi, 2 pi radians. Not 2 pi times r, just 2 pi radians. Okay? Divided by 1 day. Or you could say 24 hours. Or you could put whatever units you want out there. It could be seconds. You could convert this into seconds. We could say that the Earth revolves around the sun in 365 and a quarter days. 365.25. You all know it's not exactly 365, right? It's not. Sorry. It's actually 365.25, which is why eventually it adds up, right? Because if you're, what do we say? How many days in the year in our calendar? 365. You all know this, right? 365. So we're chopping off that 1 quarter. So in reality, by the time we go all the way around the sun, okay, we think that we say on the calendar, yeah, we're right exactly where we are around the sun that we were a year ago. And the answer is no, you're not. You're just a little bit short of it. You're actually right here. If you were to go 365.25, then you'd be at exactly the same spot. But if you say, oh, but we cut our calendar short, and we say right here, 365. Okay, so we're pretty close to where we were in space. Not exactly, okay? That's not a big deal, except for the fact that time just keeps moving forward.
Is this how we get leaky?
Ding, ding, ding. Because if you do it another, if you do it again, okay, then the next year you're even right there, okay? And eventually another year you're right there. And if you do another year, you're right there. In fact, you are after 4 years, you are 0.25 plus 0.25 plus 0.25.
A whole day.
You're a whole day short, okay? Of where you were, okay?
Wow.
Is that making sense to you? So that's why what you do is you say, all right, on this year, we're actually going
to add a year to
we're going to add a day.
We're going to add a year to our year.
And so now it puts us right back here. Does that make sense? Okay, well now you know mathematically.
See, I was always
why there was
they always just told me we have an extra day. It's fine. And I was like,
was it cool?
And I was like, 3rd grade. And I was like, okay.
For the people that were born on that.
Yeah. All right. Now there is something else though that this is actually not totally exact. Okay, because it's not exactly 365.25.
Oh, it's like 13 more decimals.
Yes, there are. Okay, and so what the problem is that there's actually a little bit more information. It's like a 1, 2 or something like that. Okay, so in reality, we're off by by this, and so we're like, okay,
We're just.
so we need to add another, so we need to add a day, but if we add a full day, we can't do that. So what you have to do is you have to add in, it's like every 100 years, then it's not a leap year, but then every 400 years it is a leap year, because eventually what happens is that this little error right here, if you keep doing this, it adds up, and so actually it ends up pushing us too far ahead here, okay?
My mind is not powerful.
I'm serious, and so every 100 years, you don't have a leap year, unless it's divisible by 400, in which case you do have a leap year.
It's what, the year?
Yeah, because every 100 years you keep doing good, but then every 400 years, then you pull it back a touch, and that's how you start compensating for all this other stuff. It's a little bit beyond us right now, but
I love space. I love learning about space.
so anyways, that's
Space is so cool.
you also end up they have these things called leap seconds. Okay. And that's to be able to compensate for the time. and stuff like
Leap
that.
seconds?
Yeah, there's leap
So like
seconds.
61 seconds in a minute?
Well, no, like sometimes at the end of the year they will actually they will hold the clocks for 1 second to make up for different things.
3,
The world clock.
2,
Yep.
1. Wait.
So yeah, exactly. Yeah, gotcha. So this guy.
New Year's Eve, like a ball.
We
Alright,
had a
well,
malfunction.
Goodbye, Robbie. We're recording. Our tapes will be there. Our cameras are here. Anyway, there's a whole lot of really neat stuff, but the thing is that it all follows certain rules and laws, stuff like that. And this is something that you have to take into consideration if you're like writing programs or software or something like that deals with dates, which pretty much every software does. You want to think something in the future, something in the past. You want to deal with that, so you've got to figure out if it's a leap year, is it not a leap year, what do you show, what do you don't show. And so there's a lot of interesting code about that. Speaking of the 100 and the 400, my programmers, what tool would you use to figure out if the number was divisible by 100 or 400? Modulo, right? You're saying percent, you're doing the percent symbol, which is the remainder division. Yep, that's exactly what you would use. Alright, so you might look forward to a program on that in the future. Okay. There is another way besides this that sort of is a hidden angular velocity mechanism, and that is, maybe we'll just leave all these formulas up here. Sure. Hertz.
Oh yeah, hertz.
Okay. So something might say it is rotating at a rate of 5 hertz. Something is rotating, or something is switching, or something is going back and forth. Okay. A hertz is a time period. Okay. So if we say that this circle is rotating at a rate of well, if they just say 5 hertz, they say 5 hertz, or this is changing at 5 hertz. What it means is it's changing back and forth. Hertz is 1/seconds, so it means 5 cycles per second.
So it's super fast.
Yes, it would be like, well, anybody music? Okay, so, well, you really don't have 1/5 notes. What about, let's say 4 times a second, okay? Okay. So, that would be like, I'll say 1 Mississippi, but it'd be like 1 ta-ti-ta. So you 1 ta-ti-ta, or 1 lolly. Do you ever have that? You all play piano? You all do that?
Yeah, but I don't.
What do you do? How
Are
do
you
you
talking
count?
about like a measure?
Like a quarter note. Like how do you count quarter notes?
1, 2, 3, 4, 1.
Okay,
Like
8
for
notes.
each measure?
Everybody what about 16th
Oh,
notes?
16. Oh, 1 E and a 2 E and a 3.
1 E and a 2 and a 3. Okay, that's how y'all do it. Okay, that's fine.
I was like,
Yeah, I have lollies for the third. Yeah.
okay.
1 ta-ti-ta. Yeah. Okay, so yeah.
Okay.
Anyway, so 4 accounts. 4 hertz would be 4 times a second. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So that's 4 times a second. Other cycles and stuff like that. If you have megahertz, if you said 4 megahertz, MHz, mega means a million. Okay. So that means you've got 4 million cycles
Oh my goodness, that's a shit.
per second.
Holy crap.
All right. Does anybody know how fast the modern computers are? This is not how fast your cell phone might be in the megahertz, but how fast like a computer? Anybody know, John?
30.
30 megahertz?
Probably.
No,
I think it's 120. I heard 120.
120?
No.
No.
I'm not sure.
All right.
He's like, never mind, that was wrong. I heard it from somebody. Someone that was stupid,
I know
so
it's
that's not
megahertz.
right. Certainly didn't hear it from myself.
All right. Modern computers are going to be around 2.4 gigahertz.
Oh my
Gigs.
gosh.
Okay. Now there's gigs, which is in terms of memory. Okay, but I'm not talking about memory, how much space you can store for your videos and stuff like that. I'm talking about something called clock speed. All right. So if we have 2.4 gigahertz, anybody know what a giga is?
Gigabyte.
Good job.
What is that relationship in terms of millions? It's a billion.
A billion.
Okay. So
Oh man.
when you look at a computer, okay, and it says that this is its clock speed is 2.4 gigahertz. There's actually a crystal in there or something that's changing polarity. It's going back and forth. It's changing 2,400,000,000 times per second.
Wow.
Okay, or give or take a couple 100,000 maybe. So anyway, that's how fast your computer is switching back and forth, back and forth. And what that's doing is it's sending a signal to all the other parts of the computer saying, change, 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 send the data, send the data, send the data, send the data, send the data. And everybody is like all in lockstep, like they're all connected like beads on a string, and they're all like, okay, okay, okay. And then when it hears that click, then it from the clock, then it sends the information, and then when it hears the next one, it says okay, I'm going to stop sending information. Send it, then stop, then send it, then stop. And so this is the drummer beating the drum that everyone hears to know to do what they're doing at the right time. So anyway,
Wow.
that's cycles per second. If you were talking about something that was spinning, okay, you might have something that's spinning at, I don't know, if you've ever driven a car, or have a friend that drives a car, or your parents drive a car, there's the speedometer, but then there's that other little thing that moves back and forth, and normally it goes like from like 1 to 9.
Oh, the RPMs.
Yeah, the RPMs. All right. And normally it says something down here at the bottom, like times 1,000.
Yeah.
Okay. So what is RPM? Well, that is an angular velocity. Okay. All right. Just to be clear here, when I was talking about cycles per second, something's not literally spinning that many times. It's actually just going back and forth.
Okay.
Okay, it's going back and forth. But they'll say cycles per second, and we might see that on some of these problems. Okay. So if your car is the needle is right here between 2 and 3, so that would mean about 2.5 RPM. Now it's times 1,000, so it really means 2,500 RPM. What does R stand for? Rev. What does P stand for?
Per.
And M? Minute. We'll do this problem over here so it's a little more visible. So 2.5 RPM. What we're going to do is we're going to convert that into radians per second, since that's a very common unit that we want to turn this stuff into. So 2,500 I'll get rid of that dot, which is somewhat misleading. Revolutions per minute. And we're going to convert that into radians per second. So we're going to have to do some multiplying. I'm going to need to turn that revolutions into radians. So I'm going to have to do some sort of multiplication. And then I'm going to want to turn those minutes into seconds, which is going to involve another multiplication. So here we go. I want to cancel out the revolutions, so I'll put revolutions down here. I want the actual units to be in radians, so I've got that up there. Now let's think about what is the relationship between revolutions and radians. 1 revolution is how many radians? 2 pi.
Oh, snap. I gotta think.
That'll cancel out the revolutions. Then I want to get rid of minutes, so I'll put minutes up here to cancel, put seconds down here. And we all know that 1 minute is equal to 60 seconds. And since you have a calculator, we then can multiply straight across 2,500 times 2 pi times 1. And then divide by 60 times 1. So just divide by 60. And then that will tell us how many radians per second the axle is spinning in our car. And it says 2.5. You got a number? What do you got?
What am I rounding to? We're not rounding.
10. Here's 10, sure.
130.9.
Anybody agree or disagree?
I didn't do
Well, maybe I did it wrong.
No, we'll find out.
I did it by pi instead of 2 pi.
That's fine.
that. I got 261.
Oh, okay. Oh, yeah, okay. I agree.
Yeah.
So, yeah, pi instead of, okay, so yeah. So 261.8, I agree.
Okay.
Okay, is that a realistic number?
Sure. Maybe.
Yeah, I'll be honest, I don't know either. I mean, the math seems right, but I am not very comfortable or familiar with radians per second. You know, like I'm comfortable with miles per hour. I can probably tell you if I'm going 20 miles an hour, 60 miles an hour. I don't know if I could tell you if we're going 20 radians per second or 60 radians per second. Okay, so better make sure your math's good on that. Okay. All right, let's go and look at some problems. See if any of this stuff that we talk about is going to be helpful. Number 7. Jupiter has a diameter of 88,846 miles. As the planet turns on its axis, so we're talking about this diversion here, a point on its equator travels at 669,883 miles per day. That's how, so if we were to track that from the time that there's a point on the equator, I'll be Jupiter in this situation. So here I am, big, huge, biggest planet. It's a gas giant. All right. So point there on the edge is as it spins, right back there at the beginning. That point would have traveled during the course of the day 669,883 miles. Okay. Now it's not actually traveling around Jupiter. It means stay in one spot, so to speak, but if we were to take that whole circumference, so to speak. Find the angular speed of a point on its equator in radians per day. Find the number of rotations the planet makes per day. Okay. The number of rotations the planet makes a day, doesn't it make sense to just make one rotation?
Right?
I don't know, something seems weird about that one. Okay. What are they asking for here on part A? Find the angular speed. Do we have a letter or variable that we use for that, for angular speed? Omega. Okay. And looking at our formula, we have omega equals theta divided by t. Another formula that we've got at our disposal is the velocity equals r omega. Not sure which one of these we're going to use. Maybe we use both. We'll kind of go with that. Let's look at the other piece of information. We have a diameter of 80,846, which implies that our radius is 44,423. Did that all in my head. Isn't that amazing? Okay. And the point travels 669,883 miles per day. What does that number look like? That's how far it's traveling all around the edge. What quantity would y'all say? Some of the options are S, R, theta, V, R, omega. Something per day, miles per day. That is a velocity. travel this many miles per day. Technically it's a linear velocity formula. Okay? Alright, so find the angular speed. So that seems like, looks like we might want to use this formula right here, okay? Because I have the linear velocity and I have the radius and I want to find omega. Okay? So I'm going to manipulate this real quick. I'm going to divide both sides by r. So omega equals velocity divided by r. So omega equals 669,883 divided by 44,423. Alright, so what number do y'all get when you do that?
15.1.
Say again? 15.1? Okay, but now we've got this issue of what in the world is this, are the units here? Okay, I'm going to write this a little bit, write it out a little bit more clearly. 669,883. The units there are miles per day divided by 44,423 miles. So the way that we handle the units here is what we'll do is we'll split this problem up, okay? We'll deal with, we'll write the 669,883 divided by 44,423 times, and I'll write miles per day divided by miles. So this is, they do this in your science classes. I saw this a lot in college, where you just would do all the numbers, and then you would do all the math with the variables over here. Okay, so then you can figure out what the units were. So do we have agreement on this, that it's 15.1 for the numbers? Okay, so now let's figure out what's going on with these units. Okay, so I have a fraction. We kind of treat this sort of like algebra. Miles per day divided by miles. Well, I don't like fractions of fractions. I'd rather do miles per day times, so the numerator times the reciprocal of the denominator. 1 over miles. So far so good? So those cancel. And so I've got 15.1 something blank per day. Right? Right? And what is it up here? It's radians. Now, you say, it seems like you sort of waved your hand there and called it radians, and I did. I can't remember right now why we put radians in there. Yeah, but you can't just like all of a sudden insert radians in there. Just be like, radians, these radians. But that's what we'll do for right now, because if we look at the back of the answer packet, the answer is 15 radians per day. Okay, that's pretty good. Find the number of rotations the planet makes per day. Now, what in the world does that mean? I'm looking at the answer here, and it says two rotations per day. I need somebody that kind of knows about planets here. I mean, they're telling us that it's 2, right? It makes 2 rotations per day. Well, wait a second. What's a day?
Well, in context to us, or my mind is not.
Yeah. That's where we're going with this. What's a day, folks?
Depends on which planet.
A
Ding,
rotation.
ding, ding. It depends on which planet you're on.
Rotation around the sun.
No. There's a
Jupiter.
this thing when it goes around in its own little circle, when it spins around. Boom. That is a day. Then there's
The year.
revolving around the sun, right? Okay, actually I should do this. I should be doing this.
You should be, yeah.
Right? Okay? I'm not going to do that 365 times. I'm busy after 3.5 times. So that's revolving around the sun. So we're talking about 1 rotation all the way around. That would be a day. Okay?
But if it makes 2.
Then what that means is that what they're referring to as day here
our
cannot be
day.
a Jupiter day.
Oh.
Because then the answer would be 1. Okay? How many rotations does the planet make in 1 Jupiter day? Okay? And the answer is 1. It makes Jupiter makes 1 rotation in 1 Jupiter day. But how many rotations does it make in 1 Earth day?
Oh, okay.
Okay? In 1 24-hour period.
I was like, for a second, my mind was.
Okay? So, what they're asking is number of rotations per 24 hours. We should probably write it like that. How many rotations in 24 hours? Okay? So now we already know the answer, but we're now going to figure out how to get there based on all of this. Okay? So according to this last piece of information, 15.1, they want us to round to the nearest whole number. Okay? So 15 radians per day means 15 radians for every 1 day. Okay? So we could write that, I guess we could also say in 1 day or in 1 24-hour. Would you rather, I could say 24 hours, it travels 15 radians. So the question is, 15 radians is how many revolutions? Alright, so here we go. 15 radians per 1 day. I want to convert that to revolutions per day. Does that make sense? Go and figure out how many revolutions it has per day. So the day is fine. It's staying where it is. I want to get rid of radians, and I want to turn that into revolutions. So 1 revolution is 2 pi radians. Alright, so let's do that. 15 divided by 2 pi. You are doing 15 divided by 2 times pi. We need 15 divided by 2 pi.
23.6.
Say it again?
23.6.
Same problem. When you are typing in the calculator, you are doing 15 divided by 2 times pi. That is going to be 15 divided by 2, which is 7.5. Then you're going to multiply it by 3, which is about 21 and some change. So it's going to be 23. That is not what we're... So, you're doing the same thing. Observe up here. I put the parentheses here. You need 15 divided by 2 pi.
2.38.
Yeah.
2.38. Because 2 times pi, 2 pi is about 3. So 2 times 3 is about 6. 15 divided by 6 is a little bit more than 2. Okay? This is the right answer, 2.38. Now, they want us to round. Here's the whole number, 2. Does about 2 revolutions per Earth day. Okay? Tricky. Does anybody have any questions about how we did a little bit of conversation and kind of trying to struggle through what exactly was asking for, but in the end it wasn't too bad. They just want to convert that radians per day into a revolutions per day. Make a note, you might need that when you work on these problems. Let's keep going. Number 8, a ceiling fan has 15-inch blades. So the radius of the circular fan is 15 inches, in case you didn't get that. Suppose the fan turns at a rate of 48 revolutions per minute. Find the angular speed of the fan in radians per minute, and find the linear speed of the tip of a blade in inches per minute. Okay? So let's go through. We've got a radius equal to 15. This 48 revolutions per minute. What do y'all think that quantity is referring to? I'll give you two options: linear speed or angular speed. Angular, yeah, because it's revolutions, which is an angle type measurement. If it was like in inches per second, that would be a linear speed. So yeah, angular speed or angular velocity. So that's your omega. They say, part A, find the angular speed, ding ding, same thing, in radians per minute. Oh, this is going to be easy. I'm just going to take this quantity right here, and I'm going to do some multiplying conversion in order to get it over here into radians per minute. All right? So I want to cancel out the revs, so I'll put rev down here. I want it to be in rads, so I'll put rads up here. And then I've got 1 revolution is 2 pi radians. Cancel. So 48 times 2 pi. .302. 302 radians per minute. Check. Part B. Find the linear speed of the tip of a blade in inches per minute. No big deal. Linear speed, that is referring to V. So we've got V equals R times omega. So my R is 15. I'll put 15 inches times, now I've got some options here. I could use my revolutions. Now I want to use my radians per minute. So I'll say 302 radians per minute. So multiply it out, folks. 15 times 302. Okay. And the units, observe, I'm going to do something crazy again here. Inches times radians divided by minutes. See if that makes sense. So I wrote the inches right there, and I have the radians, and then I have minutes. Now, what do they want the answer in?
Inches per minute.
They want it in inches per minute, okay? Well, I've got inches right here and I've got minutes down here. The problem is I've got radians right up here, okay? So, abracadabra, wave my hands, I'm going to wipe out the radians. And it just becomes inches per minute. Wait, you can't do that? All right, you can't just decide you don't like that term in there. With radians, you can. With radians, you can add them or take them away. Now that's not the best explanation.
You know what? It just be like
When
that.
we're converting from angular motion into linear motion, then the radians will disappear because we're no longer talking about radians. And when we were converting from linear motion into angular motion, then we insert the radians. Okay? Now that's just a description of what we did. That's not really still the reason why, but I'll get back to you on the reason why. Okay? But as you can see here, we're going from omega to V. We wiped out the radians. When we're going the opposite way, we inserted the radians. Okay? We'll just keep that in mind. We'll go ahead and just analyze this one. We might not solve the whole thing. Number 9, Ferris wheel at a carnival has a diameter of 76 feet, so we can figure out the radius if it needs to be. Suppose it turns at a rate of 3 revolutions per minute. We'll write that down. 3 revolutions per minute. Talk to me, class. What sort of a value is that measuring? 3 revolutions per minute. Angular velocity or angular speed. Yeah, it's an angular thing. It's an omega. Okay? So that's why I say omega is revolutions per time or radians per time. If it's a linear stretch, like inches per second or inches per minute or whatever, then that's the linear velocity. Okay? I want to just wave my hand at these other 2 problem types. Just to let you know, these other types that I'm kind of showing you that you can solve are literally, just hold the papers right now for 1 second, what I would call plug and chug problems or substitute problems, okay? Where this is going to give a situation like a mass on a spring is moving in simple harmonic motion at time t, the height h of the mass above the rest position is given by that formula. Find the height, ding ding ding, that guy right there, when A is 9.1, W is 6.1 radians per second, T is 2, and C is 5.4, okay? I'm not really going to spend a whole class period telling you how to plug numbers in, okay? But it's got the cosine there, so that kind of has that. And there's another one on the back. It had a very similar situation. This is showing you the horizontal distance. We call it the range that an object will travel if you fire a gun, a little Nerf gun or something like that. Or even if you launch a ball, or if you get a tennis racket, tennis thing, or a softball launcher, or I don't know, catapult. If you want to figure out how far something travels given its initial velocity and the angle, then this is the formula. And they're going to tell you, hey, plug in 9.8 for G, plug in 80 for V naught, that's its initial velocity, 4 pi over 9 for theta. So this is kind of showing you the beginnings, and we'll do some experiments, we'll do some fun stuff later on relating this stuff. Right now, just you can do these types of things where you're plugging in the numbers. All right, there we go. That's angular velocity, rotation.